Hello, am I audible? Am I audible? Hello. Okay, so right now there are only two students in the meeting. So I'll just continue now and let's see if anyone joins. And if they don't, then the recording will be available. They can watch it later. So welcome to the seventh session, problem solving session of the NPTEL course, Design of Power Electronic Converters, which is taught by Professor Shabari Nath from IIT Guwahati. My name is Saleh Khan. I'm a PhD student at IIT Delhi, and I will be conducting these Saturday sessions for the NPTEL problem solving sessions of this course. So, in the seventh week of this course, the main topic was EMI, which is electromagnetic interference, and an introduction was provided to what is EMI, why does it occur, what is the disadvantage, how it is measured, what are some of the standards that are used to limit EMI, and then EMI in power electronics, how what causes specifically in power electronics, what is the cause of EMI, what are the different paths for EMI conduction, and then some design solutions to EMI uh, that can have different efficacies for reducing EMI. And then finally, one particular design solution, which is EMI filter, was focused in some detail. So I'll just, before I start the summary, I'll just mention that this is not something that I have studied in depth personally. So, uh, so if you have any questions and if I'm not able to answer, I'll try to answer in the next week and try to find out the answers for you. So I'll just summarize what was taught in the lectures. So EMI stands for electromagnetic interference, and it is essentially the disturbance that uh, an electrical component faces due to electromagnetic effects. So electromagnetic effects can be inductive effects where uh, a current carrying component produces a magnetic field that will lead to some electrical currents in another circuit, and so, or it can be a capacitive or electrostatic effect where voltage difference between 2 points, it can lead to some currents between the 2 points. So when this happens in an electrical circuit, it can lead to some problems. It can distort communications, it can disturb the normal operation, it can lead to uh, noisy operation, it can lead to more losses, and it can lead to damage in some components like in motors. If there are some electromagnetic interference there, it can lead to damage in components. So we basically want to limit this interference as much as possible. So to understand how to limit that, we first have to understand how uh, this electromagnetic interference is generated, how it is carried from one component to another. And there are basically two mechanisms for transfer of this electromagnetic interference. One is conductive and another is radiative or radiated EMI. So conductive EMI will basically be carried through wires or through capacitances, through inductances. So for example, there will be, uh, if there are changing currents, they will lead to magnetic fields, which will lead to induced currents in another circuit. So this would be an inductive type of conductive EMI. Similarly, if there are voltage differences between 2 points, they will there will be some parasitic capacitance between them, and the voltage difference will lead to, and if the voltage keeps on changing, it will lead to capacitive currents. And so these are the mechanism of conductive EMI. And then there is radiative EMI, where the different conductive elements of two different circuits or portions of circuits, they form antennas and receivers, so they radiate this interference, and another one, it one transmits the interference, another portion receives the interference. So this is another mechanism of EMI transfer, and these have different uh, magnitudes and as well as frequency ranges. So for example, here it was shown in the course that uh, if we go from very low to high frequency, so at the lower end of the frequency, we first encounter what is called harmonics. So for example, if we have a grid connected application or even a motor drive, some AC application, we usually have 50 hertz or 60 hertz voltages for grid connection. And then we first encounter some harmonics, which are basically multiples of this fundamental frequency, 50 hertz, 60 hertz. And these multiples, they will distort the voltages and currents of the grid. And similarly, in motor drives, they will lead to some pulsations in the torque, so the motor will not run very smoothly. And so these are harmonics. But what is our concern here in this portion of the course is not the harmonics part, but the EMI part, which occurs at much higher frequencies. So EMI usually happens due to switching frequency, uh, the switching of the power electronics, as we'll see, and so it occurs usually in this in the range of switching frequencies and above it. So because of the parasitic components, there will be some more resonances happening at higher frequencies than the switching frequency, and then they will lead to conducted and radiated EMIs. So conducted EMI usually happens in the lower range of this frequency range that we see here. So from 150 kilohertz to around 30 megahertz. And these are not precise lines. So it is just majority of conducted EMI will be in this region. Similarly, for the radiated EMI, it happens above 30 megahertz and up to 1 gigahertz or even higher. And so what we want now is for our converters to have electromagnetic compatibility. That means they should satisfy the limits that are set by different standards, uh, so that the converter should not emit uh, more EMI than what the limit states. So the standard will give a particular limit for different frequencies, and our converter should be compatible. EMC, it should be compatible with those limits. And this to have to satisfy these conditions for the standards, we can uh, basically try to limit the EMI at different points. So the converter here would be the source of the EMI, and then there will be a transfer or coupling path for from the EMI to, let's say, the grid or some communication line or some component where we don't want the EMI uh, uh, to basically get affected, and then there will be that component itself. So the source and the coupling path, which can be a wire or some uh, it can be limited by the enclosure, and then the receptor would be the actual component like a telephone line or a grid network. So all of these we can try to limit the EMI from the source. We can try to limit the EMI that is conducted in the coupling path, or we can try to shield the receptor itself so that even if there is some EMI in the source and the coupling path, the receiver will not receive the EMI by some shielding effect. But here in this portion of the course, we'll only talk about how the source is conducting the EMI and how we can limit the EMI by at the source itself. So EMI is usually measured in decibels. So depending on which quantity we are measuring, it can be either decibels of voltage or current or power. And mostly it is done for voltages, and even for voltages it is done for microvolts, because uh, the EMI that is conducted is in the the actual voltage is very small. So the way we find the decibel in microvolt is we find the voltage in microvolt and we take the logarithm of that, the logarithm base 10, and then multiply by 20. So then we get the decibel in microvolt of the EMI. And for conducted EMI, it is measured just decibel microvolt. For radiated, it also depends on how far we are from the source of EMI. So that is why it is measured in dB microvolt per meter, depending on how far we are from the source of the EMI. And then we can measure different quantities. We can measure the average of the EMI uh, of the radiation or the interference, or we can measure what is called a quasi peak of the EMI, which basically also takes into account how fast the EMI is changing. So, for example, in the lower waveform, you can see only two cycles are there. So, and the top waveform, there are three cycles. So, even though these can have same averages, like two waveforms of different frequencies, they can have same averages. But if we want to also include the frequency aspect in our measurement, then we use something called that quasi peak, which also accounts for how fast it is changing. So for a signal having a higher frequency, or it will have a higher quasi peak. So so these are some of the measurements that can be done. And how the measurement itself is done is we have so it depends on how accurate you want the measurement to be. If you want a very highly accurate measurement, we usually have a separate room where it is the room itself is shielded from external EMI, and then the device that whose EMI we want to measure, it is kept on an electrically insulated table, and it is connected to something that is called a listen, and we'll see how what it looks like. And then outside that room, uh, the AC supply is provided, and we take measurements from the listen to a spectrum analyzer. The listen is basically stands for line impedance stabilization network. It uh, it essentially acts as a low pass filter, and it takes all the EMI through it, and then it provides a matching network, which known impedance, which can be used to measure this EMI. And this is how the measurement will look like. It will, at different frequencies, there will be different amplitudes that will be measured. And then we have different standards for EMC. We want our device or converter to be compatible for electromagnetic interference. These standards must be satisfied depending on where you are. They have different standards. And for example, this is one standard, CSIPR 22 for class B, which means at residential areas, and this specifies the limit for the average measurement. And you can see at different frequencies the limit is different. For lower frequencies, the limit can be higher, and then for medium frequencies up to the conducted range, it has a particular level, and for higher than that, let's say in the radiated range, there is some different limit. So the measurement that we do should fall within this limit. If it goes beyond at any point, then the converter will not satisfy the limit. So if you want to make a product and it does not satisfy the limit, you may not get the license to sell that product or something like that. So that is how these are measured, and what the standards, what is the importance of the standards. Now, are EMI, how is EMI produced for in power electronics? And the main feature of power electronics as compared to other is we have, first of all, high voltages and currents, and secondly, we use switching devices. So that is why these voltages and currents are have switching nature. So that means they have, at certain points they have zero voltage and zero current, and then suddenly in very short duration of time we go to very high current and voltage values. and and this fact, basically these switching voltages and switching currents are the source of EMI. So in addition to these switching voltages and currents, we also have parasitic components uh, in various parts of the circuit. For example, we will have, each inductor will have a resistance associated with it and a parallel capacitance associated with it. All the devices have parallel capacitances associated with them. They also have series inductances. And then, as we will see, these components have parasitic capacitances the with nearby objects as well. For example, the enclosure of the converter or the heatsink. And then these parasitic, so these parasitic components means there is no intentionally uh, placed component there. For example, a parasitic capacitance across the inductor means the two ends of the inductor, because they will have different voltages. So one end will be at one voltage potential and another will be at another potential. Because of this voltage difference, and because there is these 2 points are conducting elements and they have a dielectric between them, so there will exist some capacitance between these 2 points. Similarly, because every wire current carrying conductor will produce a magnetic field, so it will act as a very small inductor. So even though this is not done intentionally, we don't want uh, a simple wire to behave as an inductor, but it will have some inductance because of the inherent nature of uh, these devices. And so these are called parasitics. And these parasitics will, so for if there is a parasitic inductance, and then a changing current passes through that parasitic inductance, we know from Faraday's law that a voltage will be induced across that inductance, whose value will be given by the inductance times the change in the current, so L di by dt. And since in power electronics the di by dt is very high, and the di by dt and similarly dv by dt for capacitive portions is very high, so that is why even a very small inductance and capacitance, it will still lead to a significant voltage or current. And that is why we will have some conducted and radiated EMI in our power electronic circuits. So before how one of the ways to understand is to understand common mode and differential mode noise. So if we have, let's say, a power electronic converter here, and we have a line, a neutral, and a ground. So this is not necessarily for AC uh, converters, but also for DC converters. We'll have a positive DC bus, a negative DC bus, and that may not necessarily be the same as the ground. The ground or the earth, what we say usually is basically what will be connected. So the enclosure of the converter, or the what is called the chassis of the converter, it will be at a, we want it to be at low potential so that it can be handled without any issues, and that is what we will call as the ground potential. But the negative DC bus, which here is this line in the buck converter, this may not necessarily be at the ground potential. So the N line, the neutral or the negative line, it will have some voltage V2 with respect to ground. Similarly, the line uh, conductor will have some another voltage V1 with respect to ground, and there will be some currents through these. So here the currents that are going into the power electronic converter are defined as positive. So I1 is the current that is going into the converter in line in the live line, and then in the neutral line the current that is going into the converter is defined as I2. So then using these voltages and currents, we can define common mode and differential mode voltages and currents. So common mode voltage would be V1 plus V2 divided by 2, and differential voltage will be V1 minus V2, and this is what we usually mean as the input voltage of the converter. We are usually talking about the differential mode voltage. So V1 minus V2 would be the input voltage to the converter, but there is another voltage that uh, we have to take into account here is the common mode voltage. Similarly, the differential mode current would be uh, I1, that is going into the converter, and ideally the same current should come out of the converter in the opposite direction. So I2 should be equal to minus I1. And if that is the case, then we will have zero differential mode current as defined here. But practically what you'll see that due to EMI, there will be some current, that is same current flowing through I1 and I2 in the same direction. So that is why ICM, which is a common mode current, I1 plus I2, if I2 is not equal to minus I1, then we will have some positive value for ICM, and this current goes through the converter to the ground. And so, for example, here in the buck converter, we see a path for the differential mode current, and this is the normal current that we have studied until now. The input current from the converter, it goes through the switches and the diodes, and then from the output it comes back to the input. So if you see from at this portion, the positive at the positive DC bus, the differential mode current is from, let's say, the input source to the converter, and then at the negative DC bus it is from the converter to the input source. So that is why this is called differential mode current. For the common mode current, so now the positive DC bus, it will have some parasitic capacitance with respect to the ground or the chassis, the enclosure of the converter. Similarly, the negative DC bus will have some parasitic capacitance, and it will also have some potential differences, V2 with respect to the ground. Similarly, the switch will have some parasitic capacitance with respect to the heat sink, and the heat sink is usually also grounded. So all these parasitic capacitance will provide a path for this common mode current. And here this circuit shows the path of this current. And you can see that this portion is called, so every converter, uh, generally you can say that each converter, it will have a node that is called the switch node, where the voltage keeps on switching between some values, voltage values. For example, here, this point where the uh, MOSFET, the diode, and the inductor are connected together, this is called the switch node in the buck converter. At this point, if you see the voltage of this point, which is with respect to the negative bus, it will go from 0 to Vin and then back to 0 in each cycle. And because of this change, the parasitic capacitance between this switching node and the ground, it because these voltages are changing and there is a parasitic capacitance, it will lead to some current. And this is the common mode current, and the path is shown here. It will come from the switch node to the ground and then back through the other parasitic capacitances. So we want to limit these currents, uh, the common mode currents, as well as there will be, so there is the differential mode current that we want to occur, that is the normal operation, and there will be differential mode currents due to the electromagnetic interference noise as well. So we want to limit these different currents. And so lastly, we can uh, see there will be different frequency ranges for the differential mode noise and the common mode noise as well. So usually the differential mode noise will be at lower frequencies, and then common mode noise will be at higher frequencies. The common mode noise is usually due to the parasitic capacitances, and while the differential mode noise is majorly due to the parasitic inductances. And then we can see that the switching frequency occurs first, and thereafter there will be resonances of the The component, like we said, the inductance will have associated with it some parasitic components. Uh, the switch will have some its own parasitic components, and these will the LC will form some resonance. And lastly, the PCB will also have some uh, parasitic inductances and capacitances, which will be very less. So that is why, so if the parasitics are lower, then you will go to higher frequencies, because the frequency, for example, like a resonant frequency would be uh, the frequency, angular frequency would be 1 by the square root of LC, where L and C are the parasitic inductance and capacitance. So as the value of these capacitances and inductances reduces, then the frequency increases. So that is why for since the PCB layout, the PCB will have very low, ideally it should have very low parasitics. So that is why the resonances related to the PCB will be at higher frequencies. Now we can come to some design solutions to EMI. So how can we limit or reduce this EMI? So the first option is EMI filters, and we will see these in detail in future slides. So these are specifically designed filters to reduce electromagnetic interference. Next, we can have enclosures. So they will basically try to limit the EMI that goes out from the converter. So you must have heard about Faraday cages or something like that. So enclosure is basically what we cover the converter with. It is usually a metallic chassis or enclosure. So, and this will try to limit the interference that goes out of the converter. Next is PCB layout. So PCB layout is very important because as we see in the buck converter design, there are so the switch node will be this conductor portion will be a noisy portion because it has high DVDT. So we want to limit the size of this in the PCB. Similarly, we want to keep this away from sensitive portions of the circuit like the gate signals or the control signals. So this is done in the PCB layout portion. Similarly, we have high frequency currents in this loop of the circuit. So we want to minimize this loop so that the parasitic inductances will reduce. So all these aspects are should be taken care of in the PCB layout. Next, we can have shielded cables. So just like the enclosure will limit the noise that can come into or go out of the converter, similarly, shielded cables will limit the noise that can come out or come into the cable. So this is usually done in communication lines. You will see that they have uh, the actual conductor, and then they will have a shield across it. And this is not the insulation we are talking about. This will be a metallic kind of a shield, flexible metallic shield, which will limit the interference that can go into these wires. And another way to reduce EMI is twisting wires. So basically, we can have, if we have two wires, one will be the forward path and another will be the return path. So if they are not twisted, you can see that they will form a loop, and this loop will form a magnetic field. And this field, so every portion of the wire will contribute to the field in the same direction. So if you, for example, see here and you apply the right hand rule, you will see that the magnetic field is in the downward direction. And everywhere this is the case is the same because the current direction is the same. But now if we twist these wires, and so what happens in each individual twist, the current directions are such that uh, the magnetic field is in one direction, and in the adjacent twist the magnetic field is in the opposite direction. and this will lead to cancellation of these magnetic fields, and it will reduce the interference and the parasitic inductances. So this is why we can twist wires, two wires or multiple wires, to reduce the effect of EMI. So next, proper grounding is also important, because as we mentioned, the capacitance with respect to the ground is what uh, provides the path to these common mode currents. So if the grounding is done in a proper way so that the capacitance is reduced, or uh, the path for the common mode will be of higher impedance, then we can reduce the EMI. Next, we can also change the gate resistance to limit the EMI. So basically, we mentioned that the EMI is due to the switching voltages and currents, and it is more mainly due to the dVdt and dIdt. And the dVdt, basically it depends on the switching time of the switch, and that switching time in turns depends on the gate resistance, because when we supply a gate voltage to the device, how long it will take to turn on or turn off, it depends on how fast the CGS we are able to charge or discharge. And so that depends on the values of CG as well as the value of RG, because in this RC circuit, if we change the value of R, then we can change how fast we can change the time constant of this circuit, and that will change how fast the CGS is charged or discharged. So if we have a higher resistance, then it will take more time for the capacitor to charge. So it will take more time for the device to turn on and similarly turn off. So then we can, so even at the same voltage level, the time will change, time will increase, so dVdt will decrease. So by increasing the value of Rg, we can reduce the EMI. But the problem that is associated with it is, if we increase the time, turn on or turn off time, as we have seen in the previous weeks, the switching loss is calculated. It directly depends on the switching time. So if the switching time increases, then the switching loss will also increase. So by reducing EMI, we are increasing the switching loss. So there is some compromise to be made. Next, we also have seen how snubbers, they can be used to limit dVdt to a particular value. So uh, that can also help in reducing EMI. Next, soft switching is something that is done. We'll see in one of the problems. Basically, normally the kind of switching that we have is called hard switching, where at a certain voltage and a certain current we switch the voltages, we switch the device on or off, so it will switch in a very fast manner, and it will lead to higher losses as well as higher EMI. But in soft switching, what is done is the device is switched basically when the current through it or the voltage across it is zero or very near to zero. So in that case, so if the, for example, we are if the device is on and it will have some current, and so before we turn it off, we will have some additional circuitry or some mechanism to reduce the current to a very low value, and then we will turn it off. So in that case, the DIGT will be very less, because the value from where the device is switching off is itself less. So there are different ways to do it and different circuits. Some are called resonance circuits, and there is different types of soft switchings. But in general, soft switching will help in reduction of EMI, as well as in reducing switching losses as well. So it has both of these benefits, but the disadvantage may be that we may require additional components, and it may change the circuit operation in some ways. It may complicate the circuit uh, in some ways. So this is soft switching. Next, we have different PWM techniques as well can be used to reduce the EMI. So for example, one PWM technique is called random PWM, and this will also have different subtypes. But basically what it means, so we have seen that uh, the EMI is due to these switching voltages. And the switching voltages, if we do the Fourier transform, they will have uh, ideally, if we switch at a fixed switching frequency, then they will have uh, components at that switching frequency and its multiples. But now if we vary the switching frequency itself in a random fashion, so that so that different cycles will have different periods and therefore different frequencies, then all of the noise will not be focused on a particular frequency, but it will be diffused over different frequencies. For example, here we have the spectrum of normal PWM and the random PWM operation. So if you see normal PWM, so we have high noise at particular frequencies, and these will be like the switching frequencies and its multiples. But if these are crossing our limits and we want to reduce these peaks, one way is to have random PWM where we will basically have different switching, different frequencies, and the noise will be spread across all of these frequencies. It will not be concentrated at different frequencies, but it will be spread across. So in that way, if it is done properly, then we can actually satisfy the standards. So so this is one method, and there can be another different methods of modulation to reduce EMI as well. So finally, you can come to specifically in how to use EMI filters to reduce EMI. So first of all, a very simple method is to use a common mode choke. And so what we do here, we have the forward path and the return path, and they are wound on a core, a magnetic core, in such a way that any differential current that goes through this core, it will basically produce a magnetic field in opposite direction for the forward path and the return path. So for example, here on the right portion, you can see is the differential mode current. So one current goes into another, comes out of the other wire. And if you see the magnetic field that will be produced by these uh, two currents, for one current it is in the clockwise direction, and for the return current it is in the anti-clockwise direction. And since ideally the forward current will be equal to the return current, therefore the magnetic field will also be equal if it is designed properly, and then they will cancel the magnetic field. So ideally, for differential mode currents, which is the normal operation of the converter, this kind of a common mode choke, it will not present any inductance because the magnetic field cancels out. But for common mode currents, which are in the same direction for the forward path as well as the return path, in that case, we will have the magnetic field they will add up for the two currents, and therefore there will be some inductance for the common mode currents. And therefore, this kind of a common mode choke, it will provide some filtering for the common mode currents, but not for the differential mode currents that are the operational currents of the converter. So now this kind of a common mode choke is actually utilized in a larger EMI filter, and here is one example of this kind of a filter. So we have the converter, which is the EMI source in this case. So uh, so ideally we usually think of the converter as something that is between the voltage source and the load. But here we are thinking about the converter as a source of EMI. And then we want this EMI, it should not reach to the actual grid or whatever the voltage source we have. So that is why we will have a filter, a EMI filter between the power electronic converter and our uh, the grid or the line and neutral. And here there is a a listen that is shown for the measurement purposes, but usually you will not have a listen here. You will have just your input voltage source. And here the filter that is shown, it it is basically a pi type of filter. We have one capacitor in the beginning, and then we have some inductances, differential mode inductances, which will be the choke that we saw previously, and then sorry, common mode inductance will be the choke that we saw, and then differential mode inductances will be the normal inductances that we see. And then we have some more capacitors. So the capacitors that are connected between the line and neutral, these are called X capacitors, and the capacitors that are connected between the line and ground and neutral and ground, and this is the overall ground, the chassis ground or the enclosure ground. So these are called Y capacitances, and these are some special capacitances for EMI filters. And then we'll also have some damping portion of the circuit, because all the RC, RLC, RC or LC, these will have some resonance, uh, as a resonant frequency, and they will lead to some resonance. And if this resonance is not managed, it can actually lead to instability of our circuit. So that is why we have to incorporate some damping, whether it is done by actual resistances or some different kind of damping, which will uh, reduce those resonance peaks, and it will make the whole operation stable. So so now this circuit will have actually different paths for the differential mode currents and the common mode currents. So here on the left we have shown the equivalent circuit of the differential mode currents. And basically, since we have seen that the common mode filter will not provide any impedance to the differential current, so that is why it is not shown here. Only the leakage portion of this common mode filter will be here, and then these two differential mode inductance, they can be actually lumped together. And then for the differential mode circuit, the current path in these Y capacitors will actually be from line to neutral. They will not go to the ground. So it will just be a series combination of two CY capacitors. And then these two are connected in parallel with C in 1. So that is how the differential mode circuit is shown here. And then these equivalent circuits are basically used to analyze and then decide on the values of these different parameters, the common mode inductance, the differential mode inductance, C in 1, C in 2, and CY. And similarly on the right, we have the equivalent circuit of the common mode filter. So for the common mode, we have only the choke and the CY capacitances, and uh, as well as the differential mode inductance in two of them in parallel. So that is what is shown here. So now there can be different topologies of these EMI filters. So, so for that, how to decide on which topology we want to use, we have to understand impedances of the converter and the load, which in this case will actually be the voltage source that we have. So because we are talking about the converter as a source of EMI, so that is why it will have the V source is basically the EMI, and the Z source will be the impedance of the converter, and then we will have the impedance of the the voltage source or the current source or whatever the power source, energy source that we have. And depending on whether the impedance of this load and source is high or low, we can have different kinds of filters. So for example, if we want to use a very basic filter, we can either use a capacitor, simple capacitor, or a simple inductor. And which one to choose actually depends on the impedance of the source and load. If the source and load both have high impedances, then we want our filter to have low impedance, so that it will provide a path for the EMI, so that the EMI will prefer this path. Similarly, now if the source and load they have low impedances, then we want to have the inductor so that again it will attenuate the EMI. So because the inductor will present high impedance to high frequency noise. So so this mismatch will actually provide attenuation. Similarly, now this is for a very simple filter. If we have a higher order filter to improve the attenuation provided, then we can have a pi kind of a filter or a T kind of a filter, which will provide 60 dB per decade compared to the 20 dB by decade. And you can understand that 60 dB is actually 1,000 times more than 20 dB. So actually, so to provide the same attenuation, the this LCL kind of a filter or a CLC kind of a filter, this overall size will actually be smaller than an L or a C filter of the same attenuation. And lastly, we have a quantity that is called EMI filter insertion loss. And even though it is called a loss, it is actually a measure of the attenuation that the EMI filter provides. So so at a particular frequency, what is the insertion loss means that what is the attenuation that it provides at that frequency. And it is actually, so again, if we have the same concept where we have a source of EMI and then the load, which will be the grid or some other voltage power source. So one circuit will be without any EMI filter, and another circuit will be by inserting this EMI filter into the circuit. And then we have two voltages at the load. V2 dash is without the filter, and V2 is by having the filter. And insertion loss is defined as the uh, log of V2 dash divided by V2. So, so if this insertion loss is basically the attenuation that is provided. And then if you try to find out the expression based on by considering the EMI filter as a two-port network, you will get this equation. So now we can come to some basic multiple choice objective type problems. And I guess before that we can have a short break. So we can have a break until 4 p.m. and then we'll continue with these basic problems. Okay, so we'll continue at 4 p.m. Okay, so let's continue. So since these problems are objective-type problems and they don't require any numerical solving, I will actually ask you guys to guess the solution in the chat. So for this problem, so we have actually seen this in one of the earlier slides. So what is the answer to this problem? What is the frequency range of conductor EMI? Yes, so we basically saw that for very low frequencies from 50 hertz to 2 kilohertz, these will be the range of the harmonics. And then above some higher frequency, 150 kilohertz will be the range of the EMI. And between the EMI from 150 to 300 megahertz, it will be conducted first, and then from 30 megahertz to 1 gigahertz will be radiated. And 5 to 50 hertz is usually not encountered in uh, grid connected type of systems, but it will maybe encountered for motor drives, variable motor drives, where you want to have a full speed range, for example, in vehicles or some other application. So there we will get this kind of a very low frequency range if the speed is low. But for the question is asking about the conductor EMI, so there we have from 150 kilohertz to 30 megahertz. The next problem is radiated EMI, measurement of radiated EMI. So how is it measured? Is it measured whether using a listen device line impedance stabilization network that we saw, or using an antenna, or 2 watt meter method, or a stroboscope? So actually this we did not cover in the slides. So we'll cover. So but what do you guys think is the answer? Yes, so for uh, conducted and radiated EMIs, they can be measured using, they have to be measured using different uh, setups. So for the conducted EMI, we saw that we have in that isolated room, we will have the device under test, and then it will be connected directly to the listen device or listen filter, and then from the listen output, can be connecting to the spectrum analyzer. But for radiated EMI, we have the device and there is no connection to it, uh, to the measurement, but it is just the whatever it radiates, it is actually picked up by an antenna, and that antenna is connected to the spectrum analyzer, which is also connected to the ground. And then whatever is picked up by the antenna is actually shown in the spectrum analyzer. And then it also depends on where you place the antenna, so that is where uh, the volt per meter comes in. So depending on how much is the distance, and so that distance has to be included in the measurements. So for radiated EMI, it is measured using an antenna. The next question is which of the following is the main source of common mode noise? So the question is asking about the main source, and the options are the parasitic capacitance, wire resistance, high power levels, or long cables. Yes, so if we see all of these, they will actually have some effect on the noise. So if the cable is longer, then it may have lead to more parasitic capacitance, it may have more inductance as well as more resistance. So that may have some effect on the EMI. Similarly, if we have higher power levels, so that means the voltage and current levels are higher, then the dVdt and dIdt will also be higher. So the noise may be increased. Wire resistance, I mean, if by having higher wire resistance, it may actually provide some more impedance to the noise, and it may lead to more losses. But if we talk about the source of the noise, so once we have these dVdt and dIdt, then it is mainly the parasitic capacitance which provides the path for the common mode noise. So for this question, it is the parasitic capacitance that is responsible for providing the path of the common mode noise, and uh, so it is the main source of the common mode noise, we can say. The next question, we actually discussed this. So the gate resistance, by increasing the gate resistance, what can happen? So whether it will reduce or increase EMI, or and reduce or increase switching loss. So ideally, we would want a solution that can actually do what is it in A, that it will reduce the EMI as well as reduce the switching loss. And the worst case situation would be something that will increase the EMI and increase the switching loss. But in this case, as we saw that the gate resistance, by increasing the gate resistance, we will actually reduce EMI, because as we said that increasing the gate resistance will increase the time it takes for the CGS to get charged and discharged, and that will in turn lead to uh, different, it will lead to more time taken for the device current to rise as well as the device voltage to fall. So the dVdt and dIdt will reduce because the dt itself, the time duration, increases. So it will reduce the EMI. However, as we have seen, the switching loss is actually the product of VDS and ID for the MOSFET here. So if it takes more time from the same uh, peak point, in that case, the switching loss will increase. So because we also saw in the formula for calculating the switching loss, it is uh, the peak current, the peak or the DC current and DC voltage times the switching frequency and times the on time plus off time for the total switching loss. So somebody has their hand raised. Santosh Kumar, you have a question. Okay, so if you have a question, you can ask on the mic or you can ask in the chat. Okay, so for this question, the answer is that by increasing the gate resistance, we can reduce EMI, but it will increase the switching losses. So that is why this is not a preferable uh, solution to reducing the EMI, because it actually creates some more problems. And by increasing the switching loss, that means the efficiency is reducing as well as the temperature of the device is increasing. So the heat sink that we have designed, it has to incorporate that additional loss. So it may, if we don't increase the gate resistance properly, it may actually damage the device due to the additional heat. So that is why the other methods, that is by adding some filters or snubbers, those are better methods for reducing the EMI. But this can be done if you are very close to the meeting the standards, but you just want to reduce the EMI further, so you will slightly increase the resistance. Or if the resistance is creating some problem that sorry, the switching is creating some problem, that it is creating some noise and it is affecting the gate pulses, then you may want to increase the gate resistance slightly, keeping in mind whether the heatsink is enough. So it has limited capability for EMI. So next question is, we have to select the correct filter EMI filter combination depending upon the source and load impedances. So if the source has high or low impedance and then the load can have high or low impedance, what kind of a filter do we select? So, so in this case, if for example here it is a CL filter, so that will mean the C is connected to the source and L is connected to the load. And so you keep in mind we want to have the impedance mismatch. So if C is connected to the source and source has high impedance, whatever is connected to the source should provide low impedance. So that is the kind of combination that we will prefer. So in these options, what is the correct combination? And it can be more than one of them. It need not be only one of these four. It can be more than one. So any guesses for this problem? Okay, so let's see. So if we have, first of all, a CL filter, so that means the C is connected to the source and L is connected to the load. So this will be used when the source has high impedance because the capacitance will provide a low impedance path. So that mismatch, impedance mismatch is achieved. And similarly, the L will provide high impedance to the low impedance of the load. So the first option seems correct because the CL filter is correctly attached to the C is portion is attached to the high impedance source and the L portion is attached to the low impedance load. Now, if we reverse the situation of the source and load, then obviously we will have to reverse the situation of the filter as well, which is what is done in option B. So the B option also seems correct. So for C and D, so for C we have a pi filter, and again if we have high impedance for the source as well as load, and in the pi filter the capacitances are connected to the source and load uh, directly, then in that case that is a good option because for high impedance source and load the capacitance will provide a low impedance path, so that impedance mismatch is achieved. So C1 is also correct. And finally, again, if the source and load now have low impedance, then the filter will also change from pi to T. So because the inductances will provide the high impedance for a mismatch. So all of these options are actually correct. So all of them are correct EMI filter combinations. So again, you try to see which component is connected to the source and load, and you see whether that component has uh, impedance mismatch with whatever is the impedance of the source and load. So I hope that one is clear. So the next question is the unit of insertion loss, and this is quite simple. Yes, so it will not be watts because it is actually a ratio of two voltages in a logarithmic scale. So without the logarithm, it will be actually dimensionless, but with the logarithm, it is the dimension or the unit is decibels. So the answer to this is simply decibels. The insertion loss is given in decibels. And so lastly, this is the last question that we have. What kind of switching is preferable, or it's a fill in the blank question, that dash kind of a switching is preferable than hard switching from the perspective of reduced EMI. And yeah, so this we talked about briefly. So now let me try to explain it slightly more. That soft switching is preferable than hard switching from the perspective of reduced EMI. And hard switching, so it is shown here on the left side. So whenever the switch device turns on and off, so suddenly in a very short duration, when it turns on, the current rises suddenly and the voltage falls very suddenly. Similarly, when the device turns off, in a very short duration of time the current falls. And because these currents can have very high values, like in power electronics we can have very high values of current, and the time that it takes to turn on and turn off is actually very low in nanosecond range, or tens or hundreds of nanosecond range, or microsecond for very slower devices. Still the dVdt and didt will be very high. So that is why in hard switching, the EMI can be very high, the chances of EMI propagation. But in soft switching, what is done is, for example, here on the left waveform, the current is not, the current is actually changing in a gradual manner instead of a very instantaneous manner. And what this leads to is the DIDT actually here is very small, because it takes the whole cycle for the current to first rise and then fall. So so even though it can have the same high value of IC in both cases, but since the fall is actually very slow because of this soft switching, so in that case the DIDT will be less. So so that is why the EMI can be reduced. So another option is, instead of the current, we can shape the voltage waveform by having resonance in the voltage. So then the dVdt will be limited. So these are some examples of resonant soft switching. There are other types of soft switching as well, where so for example, in the buck converter we have the inductor current that rises and then it falls. But if we have a situation where it falls very close to zero, or actually to zero, it may be a DCM situation. In that case also, uh, because the current actually goes to zero, it may lead to soft switching, and then again DIDT will be limited because the switching is happening at a very low current. So in general, any kind of soft switching, most kind of soft switching will be preferable than hard switching from the perspective of reduced EMI, as well as from the perspective of reduced losses. But as I mentioned, they will have some other issues. So for example, the this kind of a resonant uh, uh, EMI or resonant soft switching solution, it will actually require some additional components, some additional L and C components to provide this resonance. And then it will also change uh, the the operation of the converter, the dynamics of the converter, the as well as the gain of the converter, the voltage gain of the converter. So you have to choose whether you want to use soft switching or not, depending on your requirements. So these are all the problems that we had. So if you have any questions, you can ask. I'll try to answer, and if I can't answer right now, then I'll try to answer in the next session, or you can email me. I'll try to figure out the answer there. Okay, so the fifth problem, we said that uh, the EMI filter combination, we want to see whether the the component that is connected to the source or the load, it should have the impedance of that converter should be opposite or mismatched with the impedance of the source or load. So for example, if we have a high impedance source, then we will want to connect a capacitor first to that source. so that it will provide a low impedance mismatch. Similarly, if we have a low impedance load, then we want to connect a, an inductor to that portion. So for whatever is high impedance, we want to connect capacitor first, and whatever is low impedance, we want to connect an inductor first. So now you just have to see what is this condition that is given. If the source is high impedance and load is low impedance, then we will have a CL filter. So the first letter will be connected to the source and second letter will be connected to the load. So CL filter, it will provide the necessary correct combination for high impedance source and low impedance load. Now, if we have the opposite situation where the impedance of the source is low, then we want to first connect inductor to the source. It will provide the higher impedance. And similarly, for the load uh, high impedance, we will connect the capacitor. And so this kind of a situation is where the impedance of the source and load is different. So there we will have a filter with two components, L and C components. But if we have now the same impedance of the source and load, so for example both are high, then we'll have to use, and ideally we'll have to use a filter with three components like an LCL or a CLC. And then again we have to choose that based on impedance of source and load. Okay. So any other questions? So if there are no more questions, then we can end the session then. So thank you again for joining, and next week we'll have the last session for these problem solving uh, course. Okay, so thank you all for joining.